Hey everyone. Today, I'm excited to share some fascinating news about a colossal cosmic collision. Astronomers have unraveled a chaotic smash-up between two massive galaxy clusters, where the cluster's vast clouds of dark matter have decoupled from the so-called normal matter. These clusters contain thousands of galaxies and are located billions of light-years away from Earth. In this huge collision, dark matter, an invisible substance that feels the force of gravity but emits no light, sped ahead of the normal matter. These new observations mark the first time we've been able to directly study the separation of dark matter and normal matter velocities. Galaxy clusters are among the largest structures in the universe, held together by gravity. Only 15% of the mass in these clusters is normal matter, the same stuff that makes up planets, people, and everything you see around you. Most of this normal matter is hot gas, with the rest being stars and planets. The remaining 85% is dark matter. During the tussle between the clusters, known collectively as MACS J0018.5 plus 1626, the individual galaxies mostly went unscathed because there's so much space between them. But when the enormous stores of gas between the galaxies, the normal matter, collided, the gas became turbulent and superheated. While all matter, including both normal matter and dark matter, interacts via gravity, normal matter also interacts via electromagnetism, which slows it down during a collision. So, while the normal matter got bogged down, the pools of dark matter within each cluster sailed on through. Emily Silic, the lead author of a new study describing these findings in the Astrophysical Journal, explains it well. Dark matter is like the sand in dump trucks and flies ahead. Silic is a graduate student working with Jack Sayers, a research professor of physics at Caltech and the principal investigator of the study. This discovery was made using data from several observatories, including the Caltech Submillimeter Observatory, recently moved from Mauna Kea in Hawaii to Chile, the W.M. Keck Observatory on Mauna Kea, NASA's Chandra X-ray Observatory, NASA's Hubble Space Telescope, the European Space Agency's Herschel Space Observatory and Planck Observatory, and the Atacama Submillimeter Telescope experiment in Chile. Some observations were made decades ago, but the full analysis using all these datasets took place over the past few years. Such decoupling of dark and normal matter has been seen before, most famously in the Bullet Cluster. In that collision, the hot gas can be seen clearly lagging behind the dark matter after the two galaxy clusters shot through each other. The situation with MACS J0018.5 plus 1626, let's call it MACS J0018.5 for short, is similar, but the orientation of the merger is rotated by roughly 90 degrees compared to the Bullet Cluster. In other words, one of the massive clusters in MACS J0018.5 is flying nearly straight toward Earth while the other one is rushing away. This orientation gave researchers a unique vantage point to, for the first time, map out the velocity of both the dark matter and normal matter and understand how they separate during a galaxy cluster collision. Jack Sayers explains it like this: with the Bullet Cluster, it's like we're sitting in the stands watching a car race and capturing beautiful snapshots of the cars moving from left to right on the track. In our case, it's more like we're on the track with a radar gun, standing in front of a car as it comes at us, and we're able to measure its speed. To measure the speed of the normal matter, or gas, in the cluster, researchers used an observational method known as the kinetic Sunyaev-Zel'dovich (SZ) effect. Sayers and his colleagues made the first observational detection of the kinetic SZ effect on an individual cosmic object, a galaxy cluster named MACS J0717, back in 2013, using data from the Caltech Submillimeter Observatory. The first SZ effect observations of MACS J0018.5 date back to 2006. The kinetic SZ effect occurs when photons from the early universe, the cosmic microwave background, CMB, scatter off electrons and hot gas on their way to Earth. The photons undergo a shift, called a Doppler shift, due to the motions of the electrons in the gas clouds along our line of sight. By measuring the change in brightness of the CMB due to this shift, researchers can determine the speed of gas clouds within galaxy clusters. Sunil Galwala, a professor of physics and Silica's faculty PhD advisor, recalls, the Sunyaev-Zel'dovich effects were still a very new observational tool when Jack and I first turned a new camera at the Caltech Submillimeter Observatory on galaxy clusters in 2006, and we had no idea there would be discoveries like this. We look forward to a slew of new surprises when we put next-generation instruments on the telescope at its new home in Chile. By 2019, the researchers had made these kinetic SZ measurements in several galaxy clusters, which told them the speed of the gas, or normal matter. They had also used Keck to learn the speed of the galaxies in the cluster, which told them by proxy the speed of the dark matter, because the dark matter and galaxies behave similarly during the collision. But at this stage in the research, the team had a limited understanding of the orientations of the clusters. They only knew that Max J0018.5 showed signs of something strange. The hot gas, or normal matter, was traveling in the opposite direction of the dark matter. We had this complete oddball with velocities in opposite directions, and at first, we thought it could be a problem with our data. Even our colleagues who simulate galaxy clusters didn't know what was going on, says Sayers. And then Emily got involved and untangled everything. For part of her PhD thesis, Silic tackled the mystery of Max J0018.5. She used data from the Chandra X-ray Observatory to reveal the temperature and location of the gas in the clusters, as well as the degree to which the gas was being shocked. These cluster collisions are the most energetic phenomena since the Big Bang, says Silic. Chandra measures the extreme temperatures of the gas and tells us about the age of the merger and how recently the clusters collided. The team also worked with Adi Zitran of Ben Gurion University of the Negev in Israel to use Hubble data to map the dark matter using a method known as gravitational lensing. Additionally, John Zhu Hone of the Center for Astrophysics at Harvard and Smithsonian helped the team simulate the cluster smash-up. These simulations were used in combination with data from the various telescopes to determine the geometry and evolutionary stage of the cluster encounter. The scientists found that, prior to colliding, the clusters were moving toward each other at approximately 3,000 kilometers per second, roughly 1% of the speed of light. With a more complete picture of what was going on, the researchers figured out why the dark matter and normal matter appeared to be traveling in opposite directions. Though it's hard to visualize, the orientation of the collision, coupled with the fact that dark matter and normal matter had separated from each other, explains the odd velocity measurements. In the future, the researchers hope that more studies like this one will lead to new clues about the mysterious nature of dark matter. This study is a starting point for more detailed investigations into the nature of dark matter, says Silic. We have a new type of direct probe that shows how dark matter behaves differently from normal matter. Sayers, who recalls first collecting the data on this object almost 20 years ago, adds, "It took us a long time to put all the puzzle pieces together, but now we finally know what's going on. We hope this leads to a whole new way to study dark matter in clusters." Let us know what you think about this exciting discovery in the comments. And don't forget to subscribe for more space news.